since everybody finished on time, we have 30 minutes approximately, a little bit less, for question and answer. We'd like to take, have our panelists come up on stage and take questions from the audience. Please come to the microphones in the middle if you'd like to ask our panelists some questions. Oh, here comes Horst.
Good morning. I really enjoyed the panel, but I think you deviated from the very first sentence that Josh said. Moore's law is about business, so I'd like to ask a business question to all three of you. To Josh, at this point we have possibly reached saturation of the standard PC market, and without the business case, how can Intel go forward and make the $10 billion investments in future fabs that are needed to push beyond the current limits in CMOS? It's a costly proposition, and you didn't talk about the business model. And for Damian and Karlheinz, I ask a related question. This is, how do you see the technology that you have developed in the lab move forward and become a computer business, if at all?
So, yeah, it's working. Just checking. I can't tell from where it's working. To come back to the business question, let me give you a broad view of something that's currently going on. It's a repeating pattern. Computers first came out, a few centralized machines, lots of edge processing on pencil and paper to punch cards into the machine. Then PCs came out, you started to decentralize, you had this growth of the industry outside. Data centers have started to bring it back in. We've got cell phones. But cell phones are actually starting to look a lot like dumb terminals to the original mainframes. So we've got this big tower in the middle. We're moving into another era now, which is the disaggregation of the data center. Because when we go to the fully connected model, there is no system you can design that can get the bandwidth and information into a data center for processing. You're going to see more and more pushing out compute to the edges, which will look different. And this is where machine learning and other algorithms come in. Neuromorphic might be a big deal. How do you do signal attenuation, selective attention at the edges, to send attenuated small signal information back to a data center or to aggregators for higher level processing or making larger decisions? So the question's really good. Instead of saying, well, I'm a research engineer, that's not exactly where I focus, I would say that much like everything else, there is this cyclic pattern of where you're spending your resources. And I don't see the industry as being stagnant. I see it as going through this shift to the edge, which is a very different design point than the classic PC or the tablet or even the phone.
Let me answer the question on quantum computing. Well, currently, yes, most of the things are in labs. And that needs to change. Because typically how a university lab is built up is there's a professor who has grad students who every now and then graduate and go away. And that is probably not the best way to have fast research and development of a large-scale quantum computer. And that's why, from a theory side, what we try to do currently is showing killer applications for specific cases and quantifying the economic benefit. Like, for example, I showed like the fertilizer production. That's something where you can actually afterwards say the scale you need, and you can say how much money you can make out of it. And if we have a bit more of these types of killer applications, I really believe that businesses will invest heavily in developing it. Because it doesn't take probably 10 billion. I guess $1 billion would be okay for a small quantum computer. But if you have a portfolio of 10 algorithms you want to run by that time, which can give you economic benefit, then we're good. But currently, part of the research is obviously finding new algorithms because we only have a handful. But now I think we're focusing as a research community to finding specific applications.
Okay, so for neuromorphic computing, how do we move from the lab to a new computer industry or applications that are really worthwhile to be implemented on a large scale? Now clearly the machines we build at the moment are research devices, and they have one important feature: they are really extremely configurable. And in particular, you can also read out the activity of the network because you want to understand what's going on. So these are devices which are built to understand. Now, our idea on the long-term development also to come up with products that are more compact and really exploit the energy advantage, which is definitely there, is to give up on configurability and to give up on monitoring. Because if you have a neuromorphic chip, for example, that just has the task to detect certain spatial temporal patterns, you don't really want to look as a user in your cell phone. You don't want to be able to read out any membrane potential or look at all the spike trains these things produce and look at all the correlations. You just want the thing to work. Okay? Can be trained before, and then the idea is that you use machines like that, which I see as rapid prototyping systems. So you use these machines to develop circuits that are interesting, that solve interesting problems. Then you export them, and you make a special dedicated chip that is really optimized to solve this single one problem without any configurability or monitoring capabilities. So that is for me the way. In a way, you can see the machines we build as huge neural FPGAs. Okay, they have a lot of configurability. You can implement any network architecture in your cell phone application or any application. You don't want that. You want a dedicated thing that is mass-produced and does one single thing very well. And that's the way I see it.
All right. Other questions from the audience? All right, so I'll ask a question. So the exascale program, for example, the USOne, we have a machine and the applications that deliver science are planned for. The machine comes in 23, science delivery by 2025, and that's the proximal end of the roadmap for silicon lithography. Given that we have 8 years for your respective technologies, which are various levels of maturity, where will you be in 2025?
Are you asking if I'll be an Intel employee?
I'm asking you as a private citizen.
So, I think any major company is looking at a lot of different techniques. Quantum computing is a heavy one, neuromorphic. And neuromorphic is really interesting because you could build neuromorphic circuits on top of a CMOS substrate where you're talking about analog values of decay and other characteristics. But you can also look at quantum, and these things you can simulate, as people are doing now, and as the other panelists have said. It doesn't work very well in terms of resolution of time or energy, but I can do quantum simulations, I can do neuromorphic simulations on classic architectures. But all these major companies are looking at internally, and Intel is certainly doing the same, different techniques to apply going forward, because yes, eventually turning the knob on transistors as we've been doing it will not work. When that is highly debatable, which is why I chuckled at your 1 nanometer comment. I'm not supposed to talk about how post 7 nanometer, but I can simply say that it's actively being looked into. So in the grand scheme of things, where I'll be in 10 years is hopefully standing on the cusp of something really interesting. And I don't know what that is today because we have this, as I said earlier, this horizon of maturity that whatever the next technology is, it does take 10 to 15 years to engineering-wise get it ready for mass-scale fabrication. And we don't know what that is yet, even though by your numbers, we're out of time.
Well, quantum computing in 10 years is difficult to answer. That can be anything, pretty much. It really depends on the next few years. For example, I've shown the different types of qubits we have. If Microsoft's approach, for example, works to find a Majorana qubit, that will be like probably 4 or 5 orders of magnitude less error susceptible than what we have currently. That would be a huge leap forward. If that qubit technology doesn't work, we have to reside on the ones we have. There are things we haven't yet figured out how to do. For example, when you start scaling your qubits, you have to control them. And for example, superconducting qubits, you control them by microwave pulses. But you cannot just wire millions of lines into a fridge, which has to be at 20 millikelvin, and try to control them. So what needs to be developed on the side is essentially superconducting classical logic, which can control your quantum computer. That is a very difficult task, and I'm frankly not sure how fast that will go. But I guess in 10 years, we should have a machine which is better, what we call a quantum supremacy. It will be faster than, at least it can do a calculation, let's say it like this, it can do a calculation you cannot do on a supercomputer. The question is, will it be, probably in the next few years, you might actually reach that stage already, except that the calculation will be useless. It's a calculation where we can do it, but it doesn't give us any benefit. It's not an application we want. But maybe in 10 years we can actually already solve small quantum mechanical systems, where we actually care about the solution.
Now, for neuromorphic computing, I'm actually quite optimistic, because if you really see what industry, Google, Facebook, others are doing now, is already pretty much neuromorphic computing. If you look at the deep learning experiments that people do, Google Go or AlphaGo just as an example, but many other applications, they work extremely well. And then what you see, if you watch the AlphaGo player playing against the human, you see it behaves very human-like, and also the time scale the system reacts is like a human. It takes a couple of minutes to react. Okay? It's a real game between two items, entities that are kind of equal power, or maybe even the machine is a little bit better. But what people don't see, or what Google of course doesn't tell people, is that it took something like a year to train this system. Okay? It was on a big cluster of graphic cards, consuming certainly several hundred kilowatts of power over a very long time scale, many months. And of course the system looked at many Go games, discovered the rules, and developed a structure that is actually able to play Go very well. So the problem we have in these systems is that once these systems are configured and work, they are really nice and they are ready for application. The problem is that it takes forever to train them. It's a huge amount of time and energy, and that's not very practical. And here I see is that accelerated systems, and also in particular spike-based, which is an open issue what the spikes are good for. I think we have very good arguments to say that spikes are not only contributing to energy efficiency, but also to learning speed. We have a paper out, will come very soon. If you're interested, I will send it to you. I think that the important thing that neuromorphic computing has to do is accelerate the learning. And it has to be done locally on the system. You know? And currently we have these kind of loop experiments where you have a system that you train and the system that does the evaluation of the result. But we have to implement local learning on the substrate. And we are going to do this, and others are going to do this. And once you accelerate learning, I think there will be a breakthrough for this technology, and it may change the way we do computing really fundamentally. So acceleration of learning is the key, and I'm absolutely sure it can be done on the 10-year scale, because all that needs to be done is an intellectual effort. The technology is there. We can do it with 100 nanometer technology. We are now doing 65, but it is not really important. You can use CMOS as it is. It's just a new way of using it. And you have to implement local learning, and I'm sure it will be done. As I said, it only requires ideas and intellectual input. The implementation is then, I think, relatively straightforward.
Great, thank you. Looks like we have a question in the back here.
Yes, thanks a lot for the interesting talks. My question goes precisely to the learning comments you just said in neuromorphic computing. You said earlier that you want to produce basically a neuromorphic chip and then train it offline and then port it to solve a specific task, for instance, in a mobile phone. But couldn't you argue that learning in itself, as we learn from the brain, is very crucial, especially for devices with a lot of sensors, like our human body, and to keep the system running and also adaptable to the problems.
Right.
So why don't you think that learning is also crucial for future applications that we don't currently have the fantasy to come up with?
Yeah, no, I mean, I fully agree. Of course, it would be wonderful to have the learning capability in the system that you actually use, so that the system is adapting to the changing environment. I'm just, because people were asking for a short-term and sort of straightforward application, that's where I thought that you sort of pre-train and then you use the network architecture and the pre-trained chip to really apply it just for, I don't know, face recognition on your cell phone or something like that. Of course, I mean, once we know how to implement local learning on the chip by having special processors maybe that take care of that, there is a whole new range of applications that's coming up. I mean, of course, people study that already now. For example, we have a car engine, okay, which changes all the time. It basically ages. I mean, the performance changes, and you always want to optimize the efficiency of the engine. And then adaptive neuromorphic systems would be a really cool thing to have. But it's a bit more difficult than the first approach that I presented. But I fully agree, and with the argument of local learning that I made before, it would be really, really nice to have these local learning capabilities on chip, on the system that is in the field, really being applied. It would just be a bit more difficult. But again, I think it can be done, because there are no technology barriers. That's the interesting thing here. For quantum computing, definitely there are huge technology barriers. People have to understand how to manipulate qubits. You don't have to understand how to implement transistors. You have to be intellectually clever to implement it. That's all it's needed. It needs human brain power and not so much new technology.
Isn't that true of quantum as well? It just needs human brain power to figure out how to manipulate qubits.
Yeah. But it may still fail. I think neuromorphic, I would dare to say, cannot fail because the technology is there. Maybe I'm a bit optimistic.
Do I have to change the oil after every 3,000 neuromorphic transistors?
What?
You were using the car analogy, right? My question is, do I have to change the oil in my neuro system? Right. The brain has fluid and everything else. There's doing other it decays, things burn out, they have to regrow. Some of the things that in the quantum space, right, these are burning out as devices. Right? What are you looking at in the long term? If you build a neuromorphic chip, are you going to have to deal with these things that burned out and it's no longer functional? Is it going to
burning out is one thing. Variability is an interesting topic. There are variabilities that are sort of imprinted on the system during the production process, and that's kind of static. It's fixed pattern noise on the system, and that you learn once how to handle it, and then that's it. And then there is temporal noise, of course, which kind of is a nuisance for some applications. For stochastic computing, it may even be useful. And then there is what you call burning out. That elements just stop to work. And then what do you do? I mean, what we have shown is that you can actually live with a certain degree of burning out components. There is what people call graceful degradation. If you have, for example, this classification capability, you have the insect circuit I showed. They've actually done experiments by just killing synapses randomly in the system. And the performance goes down, but it doesn't drop to zero. So you can live with it for a while. And at some point, of course, it starts to be unbearable if you lose 50% or so. But clearly there is a resilience and there is graceful degradation, which is an important feature. But I think you had another question, right? Yeah, no, you're through.
Nobody else asked the question. So far for learning on neuromorphic chips, we had a technology barrier. And that was how do you actually change the weights? And now we have the memristor discussion. So how much do you see that there is still a barrier in learning?
That's a very good question. Let me comment on how to change the weights. I mean, we do that all the time, of course. I showed the supervised thing where we change the weights by having hardware in the loop. So you have a conventional computer that measures the success and then changes the weights accordingly to some learning algorithm like backpropagation. That's kind of the most boring thing, but it works very well. Then, of course, you can change the weights by unsupervised local things, like there's this famous spike time independent plasticity, which people see in biology, and which in the bird example, which I show, is actually brought into use. But then, of course, I think if you talk about local learning, it means that the intelligence of the learning algorithm, you don't want to be off-chip, it has to be on-chip. And I can point you to a paper which we just published last week, where we propose and we actually implemented what I call a plasticity processor. So we have our neuromorphic chip with neurons and synapses. On each of the chip there is a little PowerPC processor actually, which you can use then to implement different learning algorithms in a very flexible way. Like, for example, changing the synapses, but also changing neural parameters, which is called homeostasis, and also changing the connectivity on the fly. We have developmental processes. On the memristors, I mean, they are praised very much for neuromorphic computing. I'm a bit reluctant there, because if you look to the studies that people have done with memristors, they are all the same. So you produce memristors, which are really cool devices. Hewlett-Packard has them in the lab. Then you take a probe needles and you characterize the circuit. Okay, you measure how it behaves. Then you take that computer model, it's the model of a synapse of a memristor, and you put it into a large network that you simulate on a computer. People have so far totally ignored the aspect of variability, which is, in the case of memristors, is huge. It's much, much bigger than it seems. I'm sure there are ways to handle that, but at the moment, to my knowledge, these things are not known. And I don't see how you can calibrate, for example, a memristor in a large circuit. You can calibrate a synapse of a neuron because there are parameters, there are SRAMs which actually store the parameters. So you can measure it, you say it doesn't work too well, so I fix it by loading different calibration parameters. How do you do that in a memristor crossbar? I mean, you cannot change them. They are coming from the factory, they have this huge variability. So how do you handle that? I mean, variability is not a good use per se. it can be good, but you have to put it in the right place through a learning and self-organization process. And I cannot see that people have even thought about this in the business. So
All right.
I'm very critical.
So we've come to the closing seconds of our panel here. I'd like to thank our distinguished panelists for very compelling talks, and thank you for coming to our session.